Welcome back. We have been talking about the structure property relationship of bisphenol A polycarbonates, and so mainly we have been talking about how to preserve the impact strength while we try to increase the thermal stability of the material, in other ways while we try to increase the glass transition temperature of the material. So, just a quick recap, if we go back to the script now, just a quick recap. So, if we look at the bisphenol A polycarbonate, the Tg is quite low, quite high, but as far as what we expect, if we want to increase, if we want to have very high thermal stability, then it is moderate. So, we substitute 4 methyl groups in order to increase the rigidity of the polycarbonate. So, we increase the Tg, no doubt, but the gamma relaxation temperature also is increased from minus 106 degrees or around about minus 106 degrees Celsius here to around plus 45 degrees Celsius here, and we told the ratio of Tg to T gamma actually determines that the impact strength will be retained or not. If this ratio is higher or equal to 2.52, then you will have high impact strength. In the quest of increasing the Tg, if you also increase the T gamma, then what can happen is that this ratio may become lower than this. In fact, for tetramethyl substituted bisphenol A starting material, this ratio is 1.5. So, the Tg, although it goes up to 203 degrees Celsius, a full 53 degrees Celsius higher than your parent bisphenol A polycarbonate, even then your T gamma goes up to plus 45 degrees Celsius. So, this ratio is lower, so you lose impact strength. So, what we told is that in order to solve this problem, we can rigidify the main chain in order to increase the thermal stability, no doubt, but do not try to affect this this rotation, do not try to hinder this rotation around the phenyl carbonate bond. If you do not hinder this rotation, then your T gamma or the gamma relaxation temperature remains relatively unaffected, but your Tg increases tremendously because of the restriction of mobility of this cyclohexane ring plus the restriction of this phenyl ring rotation because of this 1,3 diaxial interaction. So, ultimately then you have a high Tg to T gamma ratio. In fact, for this material you will have a Tg to T gamma ratio which is 3.1, quite high. So, you have both high thermal stability as well as high impact strength of the material. So, basically then this is your BPA bisphenol and BP, instead this is not bisphenol A. So, this is bisphenol TMC PC polycarbonate. So, this bisphenol TMC polycarbonate can be produced in the same way as you produce your bisphenol A polycarbonate. Okay. So, the same interfacial polymerization process you could use. So, you can react this monomer, the sodium salt of this monomer, you can react with phosgene and you can get your bisphenol trimethyl cyclohexane polycarbonate. Also, this phenolic OH group and the phenolic OH group or of bisphenol A. So, if you look at this molecule and if you look at this molecule where you have 2 methyl groups, these phenolic groups here in bisphenol A and the phenolic groups in this bisphenol trimethyl cyclohexane, they have the similar reactivity. So, what you can do is that since they have comparable reactivity, you can actually prepare copolycarbonates from them. You can actually prepare copolycarbonates. So, you mix them together during the copolymer preparation, and then you will have both this monomer as well as this monomer present in the polymer, and you can change the relative ratio of them depending on how you start with. Depending on the relative ratio of the monomers in the starting copolymerization mixture, you can introduce these two components in different ratios in this polymer backbone, simply because these alcohols, these phenolic OH groups here, they have same reactivity, very similar reactivity to the phenolic OH groups in this bisphenol A. And of course, if you have different proportions of these in the polymer, you can also modulate your glass transition temperature according to your needs, and that glass transition temperature you can have anywhere between 150 degrees Celsius to 239 degrees Celsius, because if you have only homopolycarbonate based on this, which is bisphenol trimethyl cyclohexane, homopolycarbonate which will have a glass transition temperature of 239 degrees Celsius. Homopolycarbonate based on bisphenol A itself will have a glass transition temperature of 150 degrees Celsius. So, if you just now make a copolycarbonate with different relative ratios, and accordingly they will go into the polymer also. So, your Tg can be varied somewhere between these two depending on what you want. So, in fact, the dependence of this glass transition temperature or Tg on the co-monomer ratio is reflected quite well in the empirical Fox relationship. So, the Fox relationship is this: 1 by Tg is equal to C1 by Tg1 plus C2 by Tg2, where this Tg1 and Tg2, their glass transition temperatures of the, so this is their glass transition temperatures of corresponding homopolycarbonates, and C1 and C2, they are basically the weight fractions of the corresponding bisphenols in the copolymer. So, this may be bisphenol A, this may be the bisphenol trimethyl cyclohexane, and this is the corresponding glass transition temperature of the homopolymers. So, weight fractions of the corresponding bisphenols in the copolymer, and then this Tg is basically the Tg of your copolycarbonate. This is how you can get your Tg, copolycarbonate. So, this is the, so let us say this Tg1 is for bisphenol A polycarbonate. So, this is 150 degree Celsius. This Tg2 is for bisphenol trimethyl cyclohexane polycarbonate, so both are homopolymers. So, this is basically how much, 239 degree Celsius. So, you change this ratio depending on what weight fraction you want for the corresponding monomer to go into the copolymer, and then from this relationship you can find out what will be the glass transition temperature of the corresponding copolycarbonate. And these are examples of a class of polycarbonates also called high heat copolycarbonates, high heat copolycarbonates. So, polycarbonate HT, like that, and these materials are tough, they are transparent, and they have high Tg. As a matter of fact, the commercially available products that reflect the technical requirements, they are usually expressed by what you call as the Weichert softening temperature. So, that is Weichert softening temperature. So, their utility is usually expressed by this Weichert softening temperature, which is directly related to the amount of co-monomer present in the system. So, if you look at the PowerPoint presentation here, so you will see, if you go to the slide please, the PowerPoint presentation, you will see that the Weichert softening temperature is plotted as a function of the co-monomer content. So, depending on how much of the relative amount of the different co-monomers, this Weichert softening temperature, or the temperature at which the material is softened, or the temperature at which the mechanical properties are lost, that can be plotted as a function of the co-monomer content. So, this is of course, this gives the utility of the material, because beyond this temperature the material cannot be used. So, you use at a temperature which is lower than that, and this temperature may be typically slightly lower than your glass transition temperature. So, this has a linear relationship with co-monomer content. You see, this is the you know what we told, this is high heat copolycarbonates or PCHT. We already talked about this. Okay. So, let us come back to our script. So, basically this temperature will determine the softening point for materials which do not have a definite melting point. Okay. So, softening point for materials that do not have a definite melting point. So, basically this is like, how do you determine this? The temperature at which the specimen is penetrated to a depth of 1 millimeter by a flat ended needle with 1 millimeter square circular or square cross section, and you are using a load of around 10 Newton to 50 Newton and specific heating rate say 50 degrees Celsius per hour or 120 degrees Celsius per hour. So, basically this is an experimental process through which you determine the Weikert softening temperature. So, what you do is that you put a flat ended needle on the top of the material, and this needle, the end of it has a specific defined cross section, and then you are putting a load on the material at the end of the needle. And so, what happens is that it's on the surface of the material, and when you increase the temperature, the material will become softer and softer. So, the temperature at which the material is penetrated to a depth of 1 millimeter, that is the temperature which you tell as the softening temperature, which you signify as the softening temperature. Okay. So, basically then the applications of these materials, if you are looking at, so already you now understand the structure property relations, the intricate details of that, why you need aromatic units, why you need certain substitutions at one position and not in another position, so on and so forth. So, typically they have outstanding, so BPA, bisphenol A polycarbonates, they have outstanding electrical insulation, good flame retardance property, good flame retardance property, they have high heat resistance. Now, you know when you are trying to minimize the size of electrical devices, minimize, so these have good insulation also, electrical insulation properties. Okay. So, when you are trying to minimize the size of your electrical devices, what you need are parts with high heat resistance. That is because when you are going to a small size, I mean when you are trying to reduce the size of the electrical devices, the different parts that you are using, they are also going to a smaller size, and the thickness of these parts also has to be reduced, and that is why you need high heat resistance for these parts, and you can use bisphenol A polycarbonate based materials for that. Okay, they can be used for housings of mobile devices, for example, also in flat panel displays or TV sets, so on and so forth. And some of the other usages, so this is electrical sector, some of the other usages could be in automotive sectors also, automotive sectors. So, because these are lightweight materials, so what you can do is that this bisphenol A polycarbonate based materials you can use, say for example, as, and also they are transparent, so you can use at headlight covers, in the radiator grills. Now, this particular application is because of the high temperature resistance. Headlight covers because they are transparent material. They can be also used as reflectors, so on and so forth. So, depending on what kind of usage you want, you would want a specific property, high heat resistance or high transparency, high impact resistance, so on and so forth. All right. So, the final thing that we want to talk about here is the flame retardant property of these materials. Flame retardant property. So, you know these kind of materials, means materials which show this kind of flame retardant properties, they are useful because you do not want, they will limit the devastating effects of fires. Okay. So, basically what happens is that when you are having a fire, typically you have an ignition source, initially you have an ignition source, initial ignition source. Now, and then maybe you So, maybe you are heating the system or whatever. So, this is the source, and then what happens is that the material that you have, this material will burn, and when it burns and then it decomposes. When it burns, it decomposes. So, this is actually your pyrolysis. So, initially you need some ignition source, and then the material will start to burn and it will decompose, and when it decomposes it will release flammable gases, and these flammable gases, they get mixed up with oxygen in air and they will start to burn. So, this fire then could be quite self sustaining after, because that also increases the heat, so on and so forth. The material burns further and it decomposes and further flammable gases are released. Now, one of the ways in which a fire retardant could work, there are different ways. One of the ways in which it could work is that it could stop the feeding of the combustion process, because when it is this combustion is going on, that it is releasing more heat, the flammable gas mixes with oxygen and it burns, it releases more heat, and then what happens, your material burns further and it is releasing more and more flammable gas, so on and so forth. So, you want to stop that feeding. So, what you can do is that you can this material that you have, this solid material, this one you stop its decomposition to these flammable gases. So, then the fire will not get any fuel and it will stop. So, basically your solid material, it will self extinguish if you can stop the formation of these gases. Okay. And what you can do is that maybe this flame retardant material can form a carbonated barrier over this solid material, preventing contact between the flame and the underlying material. It can prevent the contact between the flame and the underlying material, first of all. Secondly, it can stop the decomposition of this material so that no more flammable gas is released. This is one of the ways in which it can be done. Secondly, what can be done also, you can use a kind of flame retardant materials which can basically it can release inert gases which can mix with this flammable gas and oxygen, and it can dilute this and can reduce the devastating effect of the fire. So, what is done for bisphenol A polycarbonate is this part. So, basically a carbonated barrier, or what you call as a char layer is being formed on the surface of this bisphenol A polycarbonate, and so the flame cannot reach the bisphenol A polycarbonate and it does not decompose after, and the flammable gas is not released. So, the way it is done is the following, is through the following process. So, basically you have your bisphenol A polycarbonate, it can undergo what you call as a Fries rearrangement at this high temperature, and the product is something like this. It is it's a cross linked material. So, you will have, so this will go here. So, basically you will have this C double bond oxygen O, CH3 like this, and here you will have so you had the chain here. So, you basically have another chain that has come into the situation, and so this is a rearrangement, and this rearrangement will basically produce a cross linked material, and this cross linked layer is basically the char layer. It is a carbonaceous layer that forms on the surface of your bisphenol A polycarbonate, and then so what happens is that this material is stabilized, this melt behind the flame front is stabilized against the burning drips. Melt behind, so it is molten at this high temperature. So, the melt behind the flame front, so this char layer forms over this melt. So, this melt behind the flame front is stabilized against burning drips. So, what typically is done is that to this material you add some specific alkali salts of sulfonic acids. So, typically around 0.18%, and this low content of additive does not affect the transparency of the polycarbonate or the mechanical property of the polycarbonate, but what it does, so it is alkali salt of sulfonic acid at this high temperature of the flame front. What happens is that, so basically it is a potassium salt of sulfonic acid, it decomposes and it produces sulfur dioxide, and this sulfur dioxide is a powerful catalyst for this cross linking reaction or this Fries rearrangement reaction. So, this catalyzes this Fries rearrangement reaction at this high temperature. This small amount of this additive is added in your parent BPA polycarbonate, and this actually catalyzes by releasing sulfur dioxide, this cross linking reaction, and then the melt is stabilized from the reach of the burning drip or the flame front. Okay. So, that is the principle through which this flame retardant property of the BPA polycarbonate works. For some other kind of materials, the mechanism might be different. It might release some inert gas, say nitrogen or whatever, to dilute your flammable gas or burning gases, but this mechanism for BPA polycarbonate is different, like this, the Fries rearrangement. So, with this we have finished the details of the structure property relationship of BPA polycarbonate, and with this discussion we are also coming to the end of this course. So, we have had in the first part of this course we have discussed the principle of basically the synthesis of polymers in different ways, chain polymerization, and then we have talked about step polymerization and what not, maybe the copolymerization, the principles of those in great details we have talked about. And in the second part we started with the chemical reactors, and we discussed about different simple chemical reactions in terms of the design of the chemical reactors, the design equations of chemical reactors, and then came the polymerization reactions and how we can correlate. There is something called ignition temperature, something called extinction temperature, so on and so forth. What are the different stable steady states for say a continuous start tank reactor? Those things we discussed. Whether we use a batch reactor or a continuous start tank reactor for a polymerization, it depends on whether it is a step polymerization or a radical chain growth polymerization, so on and so forth. And then in the final part we have discussed in some detail the synthesis of different commercially important step growth polymers, and then we also talked about, followed it up by discussing in depth the structure property relationships, what kind of structures can generate what kind of properties, and how you can basically engineer these different structures in view of those properties. So, obviously, I hope you have now understood the importance of understanding these structures and how you can generate the properties, because if you do not understand the structures you cannot generate the properties, and if you do not understand how you can synthesize the structures you cannot get to those structures in the first place. So, I hope with this conclusion you have had a overall holistic view of the synthesis of polymers and their applications. And so, thank you for your attention throughout this course, and I wish you the best of luck for the exams. Thanks.